Hi, welcome back. Today we're going to talk about your worst nightmare, how to graph quadratic surfaces. Now, I am no artist, so I'm not expecting anything to be perfect on these, but we should have an idea about what these all look like when we graph, when we look at these equations. So the first step is to identify the shape. The second is to identify the center. Now, not all functions will have a center, or all quadratics have a center, but if we can find one, it will help. Next, we want to identify the main axis. This is that chart that we looked at yesterday. You can look at my previous notes. Take a look at it. We have the equation that talks about our main axes here. We'll talk about the hint on that in just a minute. Next, sketch the surface on the main axis. If a hyperbola is two sheets, we just want to identify where the vertex is. We'll talk about that in just a few moments. So the first thing we're looking at, we got this equation z equals 3. Now we should all remember that this is a plane parallel to the xy plane itself. So if I wanted to draw this, I'm going to, at z equals 3, I'm just going to put a point up there, z equals 3. Now the point's not the plane itself, but when I start drawing my plane, it's going to give me an idea, oh yeah, the plane, it'll make it more look like the plane goes through that point. So when I draw the plane, remember it's parallel to the y and x and y plane, so I start drawing a little bit below that point a line, parallel to the y-axis. Next, I'm going to draw a parallelogram on the other side, using the other side, parallel to the x-axis. And I just continue drawing my plane right there. And it looks like it kind of goes, there's a plane, and it looks like it crosses at the 3. And that's really what that point is there for. Now, it does go on forever, so sometimes people like to put little arrows right there, and that's fine as well. Okay, so the next one we're going to take a look at is one of our newer ones right here. So if you look at the graph, the function right here, the quadratic equation, the quadratic here, we have y squared plus z equals 6. So I'm going to go ahead and solve for z here. And I get z equals 6 minus y squared. And hopefully the first thing you notice is that this is a parabola. For example, this could be like y equals 6 minus x squared. So we should recognize this as a parabola, but this is going to be a parabola on the yz plane. So that's the first thing I'm going to draw. Okay, so I'm going to draw a parabola on the yz plane. This has a y-intercept of 6. If I count by 2s, 2, 4, 6. There it is, there's 6. And I know that this parabola is opening down, so it's going to open down to the y. Now, how do I know it's going to be z equals 6? Right, that should be pretty easy, right? If I let y be 0, z is 6. It's negative, so we know it opens down towards the y-axis. Draw a little bit further than that. There we go. Now, that's just in 2 dimensions, but remember we're in 3 dimensions because we have that x-axis. And if you want to, just kind of imagine like a train tunnel, because what's going to happen with the x's is that because there is no x's, that means there are no restrictions on the x's. In other words, x can be all numbers. X will take on all values. So I kind of imagine just like as a train tunnel. Well, of course it would go on forever, never, never, never. But if I go backwards, I'm going to have my parabola here. And if I go forward, I'm going to have my other parabola here. And I could go like right here. And there we go. And sometimes I'll draw like little lines right here. Again, not the most beautiful image. You should see my second try. I did it much better. But what you notice is that this is a parabola, kind of like, imagine like a parabola, and you grab it like a slinky, and you just expand that parabola. You get like a little train tunnel right there. Now, this is called a parabolic cylinder. It's called a cylinder because on the x-axis, there are no restrictions on it. So it just like extends out. Like think of like a circular cylinder, right? It goes straight up like a normal cylinder. And we can always tell the cylinder is because only one of the terms is squared. One term is squared. If another term is squared, it's no longer a cylinder. We'll talk more about, we'll see something like that. All right, so let's take a look at number 3 right here. So for number 3, again, what I'm going to notice is that, oh look, this is a hyperbola, right? This is a hyperbola. I should recognize that formula from pre-cal. but this is going to be on the YZ plane again. So I'm going to draw a hyperbola on the YZ plane. So if I can do that by, what is that? Dividing everything by 16. So I get y squared over 16 minus z squared over 16 equals 1. So on the y and the x, I'm going to go out 4 units. So remember my vertices are going to be y equals plus or minus 4. Now remember, because y goes first, that's where my vertices be. That's our rule for hyperbolas. If you forgot that, remember my vertices belong to the first term in the hyperbola. So on here I go out 4. I'll count by 2s. 2, 4. 2, 4. And I'm going to draw a hyperbola on our YZ plane. And then I'm going to stretch. Again, just like over here where there are no x's, right? The terms are squared, but remember there's missing x. Not really that there's no one term squared, it's really that we are missing a variable. Sorry. That's how we determine if it's a cylinder or not. I messed up there, so I apologize. So not only one term is squared, is that one of the variables is missing. Here there is no x, so we got to stretch along the x. Same thing right here. There is going to be no x. So now we're going to stretch along the x-axis. So this is going to be a hyperbola on the YZ plane, but we are going to stretch on along the x-axis. So just keep going in both directions. Missed. And again, we're not looking for anything perfect. Give it some definition. Draw little curvy lines right there. Makes it look a little bit better. And it kind of looks like a couple of snow plows kind of pushing away the snow there, right there. So, okay. So the next one we're going to take a look. Now we need to like some really cool ones right here. So you want to know how to graph all of these. So for the next one, if we identify the shape, now first thing I notice is that 2 are squared, 1 is not squared. So, and there's a minus there. So that's my hyperboloid of one sheet. So x squared plus y squared minus z squared equals 1. X squared plus y squared minus z squared is 1. So that's the first thing we want to know, that this is a hyperboloid of one sheet. Of one sheet. There we go. Now, z is my odd man out. Remember that. So the way we can tell which way this opens up is because z is my odd man out. This is what it opens up on. So z is negative. I say this is the odd one out. In other words, this will open on the z-axis. So let's see what this would look like. So first thing I'm going to do, I'm just going to let z equal 0. So on the xy plane, because I know it's going to open up on the z, on the xy plane, I'm going to let z equal 0. And if I do that, we get x squared over 9 plus y squared equals 1. And if you notice, this is an ellipse. We talked about this the other day. This had a special name to it. It was called a trace. If I let one of the axes be 0, or if I let one variable be a constant, and I just plug that constant in, I get a trace. So in other words, this is if I put the xy plane, sliced it through my 3D shape, we're going to get an ellipse. And I know a lot about this ellipse right here. For one, I know its vertices, or its vertices, right? They are going to be, what is this going to be? On the x's, plus or minus 3, 0, 0, don't forget your x coordinate, and on the y, it's going to be 0, plus or minus 1, 0. So I can graph it. Here's 1. On my x's, it's 3, 1, 2, 3. Backwards, 1, 2, 3. 1's on my y's, and I can draw this ellipse. So there's my ellipse. Now this is a hyperboloid of one sheet. So basically what that means is even though my cross sections are going to be ellipses, but my sides on the sides are going to be hyperbolas. So I'm going to draw a hyperbola kind of drawn like this. So I draw a hyperbola like that. And then I just draw a circle connecting them. Now, again, nothing to scale, because if you notice, this is supposed to be symmetric on the z-axis, okay? All right, it's supposed to be symmetric on the z-axis. I can never do this one right, okay? But hopefully you kind of get the idea. It's a hyperboloid, and it's one sheet because it's all connected. All right, now in college you can take a class called topology. If you ever have a chance to take a class called topology, you'll talk a lot about these type of shapes, minimizing them and everything. It's really kind of a fun shape. For example, this shape right here is like when you do those bubbles, like those big bubble ones, you stretch it out, the shape of a bubble. As you pull it from like the surface of the bubble film, the water. Anyways, kind of cool. All right, so I'm going to go and pause here, go on to video number 2. We'll take a look at some more.